The scientific method. A famous scientist once said, "Smart people can come up with very good explanations for mistaken points of view." This statement illustrates the ability of humans to conceive of excellent explanations for incorrect ideas. Many scientific explanations that seemed very reasonable once are now known to be incorrect. Without doubt, many of the things we believe to be true today will be proven inaccurate in the future. Science is constantly refining our understanding of the natural world as new data is gathered. The history of scientific thought. For centuries, people based their beliefs on their interpretations of what they saw going on in the world around them without testing their ideas to determine the validity of these theories. They used a process of reasoning called deduction. Deduction is the process of deriving conclusions from a logical starting point without resort to experimental evidence. The Greek philosopher Aristotle, who lived from 384 to 322 BC, laid the foundation for deductive reasoning, and this method was the dominant method used for scientific investigations for nearly 2,000 years. Deductive reasoning led to new discoveries in math and in other areas of science. However, it also led to some interesting scientific conclusions. For example, it was common, quote, knowledge, unquote, that simple organisms like worms, beetles, frogs, and salamanders would come from dust, mud, etc., and the food left out quickly swarmed with life. Now this may sound ridiculous, but consider the observations that led to this conclusion. Observation. Every year in the spring, the Nile River flooded areas of Egypt along the river, leaving behind nutrient-rich mud that enabled the people to grow that year's crop of food. However, along with the muddy soil, large numbers of frogs appeared that weren't around in drier times. Conclusion? It was perfectly obvious to people back then that muddy soil gave rise to the frogs. Another observation. In the cities, there were no sewers nor garbage trucks. Sewage flowed in the gutters along the streets, and the sidewalks were raised above the streets to give people a place to walk. In the intersection, raised stepping stones were strategically placed to allow pedestrians to cross the intersection, yet were spaced such that carriage wheels could pass between them. In the morning, the contents of the chamber pots were tossed out of the nearest window. When people were done eating a meal, the bones were tossed out the window too. A chivalrous gentleman always walked closest to the street when escorting a woman, so if a horse and carriage came by and splashed up this filth, it would land on him and not the lady's expensive silk gown. Most of these cities also had major rat problems, which contributed to the spread of the bubonic plague, or Black Death. Conclusion: obviously, all the sewage and garbage turned into rats. Inductive versus deductive method. About 1600 AD, it came apparent to Francis Bacon that the deductive method did not fit well with scientific investigations of nature. In order to use the deductive method, you need to start with simple true ideas about the way the world works. When you use these ideas to explain your observation to the world around you, if your ideas are true, everything that follows will be true. Bacon realized that it was enormously difficult to determine if your simple, true ideas are really true. Bacon suggested using inductive reasoning rather than Aristotle's deductive reasoning. The inductive method is the deductive method turned upside down. The deductive method starts with a few true statements with the goal of proving many true statements that logically follow them. The inductive method starts with many observations of nature with the goal of finding a few powerful statements about how nature works, laws and theories. In the deductive method, logic is the authority. If a statement follows logically from the axioms of the system, it must be true. In the scientific method, observation of nature is the authority. If an idea conflicts with what happens in nature, the idea must be changed or abandoned. Since 1600, the inductive method has been incredibly successful in investigating nature, surely far more successful than its originators could have imagined. The inductive method of investigation has become so entrenched in science that it is often referred to as the scientific method. Understanding the scientific method. It is often claimed that the scientific method of gathering, refining, and examination of data always progresses by a rigid series of steps called the scientific method. Throughout the process, scientists engaged in the investigation are supposedly objective, patient, and careful in their experimentation. However, thinking of science as using this method portrays science as an activity that is highly unnatural. Little attention is ever paid to the fact that scientists, like all humans, vary in ability, competence, dedication, and honesty. Human beings are not by nature objective. They are not disinterested or skeptical about their own research. However, they are prone to jump to conclusions on flimsy evidence and defend their beliefs irrationally. However, in spite of this, the scientific method still has value. The more closely its steps are adhered to, the better the quality of the research it will produce. Utilization of the scientific method will minimize human influences when developing a theory. Although there is no single scientific method, all scientific investigations can be said to have 4 stages. The steps of the scientific method. The heart of any scientific investigation is careful observation. The scientist observes much more carefully than the ordinary man. The scientist observes facts. Facts are things that happen, events, or conditions. These facts are recorded as data. Surprising as it may seem, there is no data that is not colored by our biases. Scientists attempt to minimize biases as much as possible. To this end, data should be precise, detailed, and reproducible. Any suitably trained scientist should be able to collect the same data. The next step in the process is the formulation of a hypothesis. A hypothesis is a statement of knowledge before experimental work has been performed. To take an example from daily life, suppose you discover that your car will not start. You may say, "My car does not start because the battery is low." This is a hypothesis. You may then check whether the lights were left on, or the engine makes a particular sound when you turn the ignition key. You might actually check the voltage across the terminals of the battery. If you discover that the battery is not low, you might attempt another hypothesis. The starter is broken. This really is not my car. The hypothesis is used to make a prediction. A prediction is what you expect to happen during an experiment if the hypothesis is accurate. A good scientific hypothesis should say not only what should happen during an experiment, but also what should not happen. The more a hypothesis forbids, the better it is. After forming a prediction, an experiment is conducted. The experimental tests may either confirm a hypothesis or rule it out. Every genuine test of a hypothesis is an attempt to prove it wrong. The scientific method requires that a hypothesis be rejected or modified if its predictions are clearly and repeatedly incompatible with experimental tests. Further, no matter how elegant a hypothesis is, its predictions must agree with experimental results if we are to believe that it is a valid description of nature. In science, experimental verification of a hypothesis is necessary. Forming a theory. A hypothesis that has been repeatedly tested and not rejected is called a theory. Accepted scientific theories become part of our understanding of the universe and the basis for exploring less well understood areas of knowledge. new discoveries are first assumed to fit into the existing theoretical framework. It is only when, after repeated experimental tests, the new phenomenon cannot be accommodated, that scientists will seriously question the theory and attempt to modify it. Changes in scientific thought and theories occur, sometimes revolutionizing our view of the world. Again, the key force for change is the scientific method and its emphasis on experiment. However, theories can never be proven, only disproved. There is also the possibility that a new observation or a new experiment will conflict with long-standing theory. For example, recent breakthroughs in the field of microscopy have provided evidence of the reality of atoms. Prior to the 1980s, we thought we understood the structure of an atom, but no one had ever seen one, so no one knew for certain. Now that atoms have been observed and direct evidence for the shape of atoms have been obtained, should atomic theory be considered factual? Even though atomic theory has been able to explain the behavior of all matter studied so far, it must be considered possible that some type of matter may be discovered that doesn't fit with atom theory. At that point, atomic theory would have to be revised or rejected. Such is the open-ended nature of science. The importance of uncertainty. The phrase scientific proof is common in the popular press, yet it represents one of the greatest misunderstandings people have about the scientific method. Even professional scientists frequently err by stating that one theory or another has been proved. The strengths of science, and the primary reason it has progressed as far as it has, is its ability to question its own findings. Science works best when its most fundamental assumptions are constantly being re-examined and re-evaluated. Scientific theories must always be on semi-probation, never being accepted without qualification, and never placed beyond the realm of further inquiry. Once a theory is accepted dogmatically, further progress on the subject is stifled, perhaps even impossible. There are several examples of scientific theories that were accepted as valid by generations of scientists, but which nevertheless eventually came to be rejected and replaced. The best known example is that of Newtonian physics. Scientists began to search for a more complete explanation of how the universe operates, which led to Einstein's theory of relativity. In any scientific experiment, there always exists the possibility that some overlooked hypothesis might be better at explaining the data than any theory already taken into account. As Einstein said, "No amount of experimentation can ever prove me right. A single experiment may at any time prove me wrong." Much of scientific methodology, including controlled experiments and rigorous statistical testing, is designed to eliminate as many alternative hypotheses as humanly possible. Nevertheless, sources of error may present themselves even before data is collected. Some may misunderstand and interpret the emphasis on uncertainty as a weakness of science. However, it is important to understand that with each new explanation, our scientific understanding of the world becomes better. Isaac Newton once said of his own theories, "If I have seen further, it is by standing on the shoulders of giants." Without the groundwork of scientists who came before him, Newton could not have gained his profound insight. To follow Newton's modest metaphor, Einstein was standing on Newton's shoulders. In the short run, individual scientists and some scientific institutions may resist change and adhere to theories longer than they should. In the long run, however, the facts eventually prevail and progress is made. Students need to be taught to question authority and think critically so they can play active roles in the progress of science. References for this reading are from John Barrow, Theories of Everything, published by Oxford University Press in 1991. J. Hatton, P. Plouffe, Science and Its Ways of Knowing, Prentice Hall, 1997. Thomas Kuhn, The Structure of Scientific Revolutions, University of Chicago Press, 1962. Joseph Leferrier, The Importance of Uncertainty, published by College Teaching, summer of 1991, volume 39 and issue 3. Bright Wilson, An Introduction to Scientific Research, published by McGraw-Hill in 1952.